You are listening to the Effective Statistician Podcast, the weekly podcast with Alexander Schacht and Benjamin Pieske, designed to help you reach your potential, lead great science, and serve patients without becoming overwhelmed by work. Today, this is episode number 82, Non-parametric analysis, much more than just a Wilcoxon test, an interview with Frank Konieczka. So today we are talking with Frank Konieczka, who is a professor at the Charitee, and he is working a lot on non-parametric analysis. And Benjamin and myself actually have something in common with him, and you'll hear about it in the episode today. Non-parametric analysis actually offer you lots of opportunities and says much more than probably the Wilcoxon test that you learned at university, or which is similar or basically the same as the Mann-Whitney U test. And this is just a two sample case, but there is much more you can do with it. And today we'll also talk about how you can describe treatment effects in these kind of situations where you don't have the usual parameter like means to describe them. So stay tuned for this really nice interview with Frank. You'll have a lot of learnings about it, especially if you're not aware of what's going on in the non-parametric field, like actually many other statisticians. One of these problems with these innovative approaches, like these non-parametric approaches, but also with lots of other innovative approaches, is that statisticians very often face problems implementing them because they can't persuade their colleagues to do these new things. There's a lot of colleagues that are very conservative and just want to do the same thing over and over again. And that, of course, leads to organization lagging behind, not reaching full potential, not leveraging what's possible. And here, statisticians need to step up and lead the organizations. Lead the organizations in such a way, not as a supervisor, but really cross-functionally influencing people. And in order to help you with that, Gary Sullivan and myself have designed the leadership program. And I talked about that already quite a lot at this podcast, but currently you have again the opportunity to enroll into the program. And the enrollment period actually will close quite soon. So if you haven't done that, check out the information on theeffectivestatistician.com/course, where you'll find all the details. You'll also find some help to talk with your supervisor about the program and why not only you, but your organization will actually benefit from it. So please go to theeffectivestatistician.com/course, and there you'll find all the information. This podcast is created in association with PSI, a global member organization dedicated to leading and promoting best practices and industry initiatives. Join PSI today to further develop your statistical capabilities with access to the video-on-demand content library, free registration to all PSI webinars, and much more. Visit the PSI website at psiweb.org to learn more about PSI activities and become a PSI member today.
Welcome to another episode of The Effective Statistician. First of all, I'm Benjamin, and I'm here with my co-host, Alexander. Hi, Alexander.
Hi, Benjamin. How are you doing?
Thanks. Very well. And we have a special guest today, coming a long way from Texas to Germany back, Frank Konieczka. He's here with us today, and we're talking about non-parametrics. Hi, Frank.
Hi, good morning. Thank you so much for having me. I'm very excited.
Yeah, it's an exciting topic actually. So we have a bit in common in a way, like in our history, because we're all coming from Göttingen. So we studied in Göttingen. Alexander did, myself, and you as well. But you are actually so young that we didn't meet in Göttingen.
We are so old.
But to phrase it positive. So that's basically. So we do have a common background, and also having the work with Professor Brunner on non-parametrics. So it's really good to have you here. But actually, my first question would have been to introduce yourself. So I already just started. Then maybe you can just give a quick introduction to yourself and just say a little bit about you and your history and where you're coming from, where you're going to, and what you're doing now.
Okay, sure. So, hi everybody. My name is Franco Nitschke. I'm professor of statistics at the Charitee in Berlin. Actually, the Charitee is one of the largest university medical centers in Europe, and I lead a research group working on statistical methods of translation, which is basically preclinical research. And let me say some words about my background. So, as being said, I studied mathematics at University of Göttingen, and I also did my PhD in mathematics at the same university, specializing in statistics. So after getting my PhD, I stayed at the same university to work at my habilitation. And let me do this a little short. After this, I got my first professor position at Ludwig Maximilians University, Munich, where I stayed for a while. Then I moved to Texas. So I worked as professor at the University of Texas at Dallas. And kind of recently, I moved back to Germany because I got a professor position at the Charitee with affiliation also at the Humboldt University and the Freie University in Berlin. And now I'm teaching here statistics and working in clinical research. And yeah, so far so good. That's what I'm doing.
Excellent.
Right now.
Excellent. So, as we're talking about non-parametric analysis or non-parametric statistics, so what actually are non-parametric analysis?
So, you could say non-parametric analysis means when you're working in statistics, you're collecting data, and what you are doing is that you work with data distributional models. Right? That's fair to say. Yeah. So, non-parametric means that you don't postulate a specific distributional model of the data. That's basically right. So you don't pre-specify that data must come from a certain distribution, for example, normality. So you relax this assumption and just allow the data distribution to be completely arbitrary.
There are also this is basically parametrics and non-parametric statistics. Mm-hmm. But what actually is then semi-parametric? I think just to distinguish between the three different types.
So semi-parametric means that you don't postulate a specific data distribution, but you allow or that you assume that certain parameters exist. For example, a mean. So when you have an analysis where you assume that a mean exists, but leave the assumption of a specific data distribution free, then you are on a semi-parametric framework.
Okay, it's basically that's a compromise.
Yeah,
that's great.
And I think here maybe the obvious question is, why shouldn't a mean not existing? And I think that is one of the tricky questions that we need to enter here, because a mean is non-existing if you can't define it because the data doesn't have the right properties. So if, for example, the data doesn't allow you to define a certain distance, for example, you can't have a mean because, well, if you, let's say, have just ordinal data that's strictly ordinal in the sense that you can just say whether something is bigger and smaller, but you can't say how much it's bigger or smaller, then you can't define a mean. So that's one situation, for example, where
where the mean doesn't make any sense, basically.
Yeah.
Yeah, for example, if data is very skewed, if the distribution is very skewed, for example, if you measure an income So income as a measure is always very skewed. Then means, for example, also might not be a best choice to define or to use as a measure of interest.
But for income, at least you can say what the mean is.
True.
It might, for certain questions, not be a good way to describe your distribution, but in other situations it might. But for example, if you, let's say, have a ratings that just describes, let's say, school gradings, for example, that, A is better than B is better than C is better than D, but it's really, difficult to say whether the difference between A and B is the same as between B and C or C and D, or whether, A to C is exactly twice the difference than B to C. So in these kind of settings, it's really difficult to define a mean, directly from the get-go. But I think that the other point is where if you have certain types of distributions, just looking into the mean doesn't make a lot of sense. So what are alternative ways we can look into that?
So we are working in this non-parametric framework usually with ranking methods. So ranking methods are a non-parametric way to run statistical analysis. So in these ranking frameworks, you are allowed to relax any distributional assumption. So all of these methods work for any distributional data scale. So this works for metric data, as we said. This works for ordinal data. This even works for binary and dichotomous data. And let me say why we are working in this ranking, or why we are working with ranking methods. It's because in many trials, sample sizes are very small. So in my area here at the Charitee, where we are working in preclinical research, sample sizes are usually very small. We have, for example, 8 or 9 measurements per group. So we have a trial where we observe a few groups and sample sizes are very small. In such a situation, you cannot estimate the distribution of the data at all. So you're always in the frameworks that you cannot get any guess about the distribution of the data. So in all of these areas, or at least for me, purely non-parametric methods are the best way of choice to run any analysis, and especially for the planning of the trial. You see, you always have an issue when you plan your trial, like an animal trial, where you will come up with very small sample sizes, where the planning is based on a parametric method, because it's very likely that the data distribution won't satisfy the assumption of the method based on which you planned your trial. So that's why I favor.
Yeah, that's true. It doesn't solve the question of power, but at least it does solve the question of distribution.
Well, I think it in that sense, it's maybe a more conservative way to calculate then the power, because you actually build in the model uncertainty, so to say. Yeah, because if you power based on an assumption that the data is normally distribution, then you might think, okay, I'm okay here because I just build in additional assumptions, and these additional assumptions then give you more power, but that's just perceived more power because you haven't built in any variability regarding your model. So and if you think about uncertainty in two different aspects, one is the uncertainty regarding the model, and then the uncertainty in the model, the non-parametric approach encompasses, so to say, both things, because there's nearly no assumptions regarding the model, or at least really, really easy to justify assumptions regarding the model. So, for example, that every subject follows the same distribution, and that they are independent. So
it's a very powerful tool, and I think it's fair to say you're always on the safe side when you run non-parametric analysis.
What are other situations where we should use ranks? So we talked about kind of the small group discussions, or when you're not sure about the distribution and kind of the ordinal approach or skewed distributions, can you think of other situations that, makes it very, very obvious or to use ranks instead of using certain parametric approaches?
Yeah, it's, for example, when you have many outliers or some extreme outliers in your data set, then ranking methods might be a very good way to analyze the data. It's fair to say at this point it depends in what kind of outliers you have. So right when you have a ranking, so ranking just means you sort the data in your list. The smallest observation gets the rank 1. If you have n observations, the largest observation gets rank n. So here, it doesn't matter how far off any outlier is from the other observations. So it can be a very robust way to analyze data with outliers. Sometimes if the outlier is very informative, then ranking methods might not be.
In these kind of settings where you actually see outliers are the important things, you would probably anyway kind of look at maybe response variables in terms of outlier, yes, no, or things like that. But I think there's also in this whole estimate framework where we have these composite endpoints in terms of where you build new endpoints and say, okay, if a person discontinues due to that reason, he gets that score. If he discontinues to another reason, he gets a worse score. And if he dies, he gets, the worst possible score. Then that's a kind of another area, these kind of composite endpoints that lends itself very, very nicely to ranks. And the composite strategy with the estimate framework is one area where ranks can be very, very nicely applied, because there you also have these ordinal data sets. So I think that links to another episode that we recorded a couple of months ago about the composite strategy for the estimate approach. And we shortly touched on this topic within that episode. So if you want to listen to that, just scroll back in your podcast player and find the episode there. Okay. One of the problems, of course, if we don't have means, for example, to describe our treatment effects and, differences between means and these kind of things, how can we then describe actually a treatment effect?
So when you work with ranking methods, it's one of the questions, so how the treatment effect, so treatment effect means it's how you can describe the difference between at least two distributions in such a non-parametric framework. So when you don't describe the difference based on means or any other model, on our model, we don't have any parameter at all. So we do this in a way, let's say we have two groups, and then we look for what is the probability that a randomly chosen observation in the first group, say, is smaller than any randomly chosen observation in the second groups. That you don't define a treatment effect based on a mean difference or on any other parameter. You just look in which of the groups are the data larger than in the other one as your treatment effect. So let's say again you have two groups. If this effect is, you look for what is the probability that any observation in the first is smaller than in the other one. If this probability is equal to 50%, right, then you can say in none of the two groups the data are smaller or larger. So it means you don't have any let's say difference between the two distribution on this probability scale.
Okay, I understand. It's just more like when you, I think that's one of the key problems, but maybe what's holding back the really breakthrough of non-parametrics in general, in the clinical trials is probably that doesn't give you like a measurement of or a quantity of a difference that you can see, because it's based on ranks and it's not based on the actual observations.
What you can say is, let's say you have a relative treatment effect of 60%. Then you know that if you're taking the new treatment, in 60% of the cases, you will be better off than taking the comparator treatment. If you have an 80% chance, then it's an 80 to 20% ratio. And I think that's actually a nice way to understand your data. And what's also nice is there's actually a relationship to the parametric case. So let's say if you assume a normal distribution and you assume that the standard deviation is the same in both treatment groups, then you'll always have the hypothesis, null hypothesis matches each other. So whenever you have a relative treatment effect of 50%, you will have a zero difference in your means. However, what's also really nice is even if you have the same mean, but the standard deviation is very different from the two groups, you still have a relative treatment effect of 50%. Yeah. So you can have, let's say, a case, let's say a very, very extreme case. You have just three outcomes for the endpoint, 1, 2, an outcome, 1, 2, and 3. And if for treatment group 1, everybody has a 2, for treatment group 2, half of them have a 1 or have a 3, you'll get the relative effect will be 50%. Because 50% of the cases you will be A is better than B, and then 50% of the cases treatment B is better than A. So for me, I think it's a very intuitive way to describe a treatment effect in situations where you just can't quantify so easily how much better it is. You can just say it's better.
Yeah, that's the limitation in that one. Yeah,
but I think the limitation is inherently in the data itself. Yeah, it's not a statistical method. Just by putting assumptions on top of it, we maybe even very fool ourselves by thinking about mean differences when actually these means don't make a lot of sense. What do you think, Frank?
Well, I think first of all, the treatment effect, you're correct. It's defined on a probability scale. So some people say it's a little harder to interpret instead of comparing means. I guess that's true. On the other hand, you base your analysis or you define this treatment effect just on saying in which of the groups the data are or the outcome tends to be larger than under a different condition. So for me, I don't think that this effect is harder to interpret. So it's measured on a probability scale. So based on the strength of this effect, you can for sure define that the larger the data will be in the second group, say, then the larger will be the probability. So larger, I mean closer to 1.
Yeah. And I think the other nice point is if you think about the binary case, and you touched earlier on that you can also apply ranks in the binary case. There's this relative treatment effect corresponds 1-to-1 to the relative risk difference. Right. So if you have response rates between in the two groups, the difference between these response rates, you can calculate that via a pretty simple formula directly into the relative treatment.
It's a major advantage also of this effect because when you postulate any distribution which has certain parameters and then compute the relative effect, then this relative effect is a function of the parameters of this distribution. And this holds for any distribution that you might think of. So as we said before, for the normal distribution, then this effect is a standardized mean difference. If you have binary data, then it's more or less nothing else than the difference between the two success probabilities. And you can continue this list for any distribution you might think of. So you always have, when you compute this effect, this relative effect for any distribution, then you can express this effect in terms of the parameters of this distribution. So I think that's a very nice property. also of this effect.
Yeah, so that's the other point. If you actually assume a normal distribution, then you can also see for a given treatment difference in terms of the means, how that relates to the relative effect in the non-parametric case. And it's just a function of the standardized mean difference then. So that's also a pretty nice way to get a little bit of a feeling for what is a big treatment effect, because you basically can calculate it back to what it would mean in a normal distribution setting.
Okay, we talked a little bit about the treatment effect. So, but as a result, how can you just visualize the treatment effect? So, how can you best present the result of the non-parametric analysis?
So, what we do and what we favor is for sure confidence intervals. So we did a lot of research in the computation and to derive formulas for confidence intervals for these effects. So you can compute those effects for any, if you have a more complex model than having two groups, you can compute these effects for all the group combinations. Yeah, and I think confidence intervals are for sure one very nice way to visualize the treatment effects.
By the way, as we are talking about that, I guess that is all described in your new book that is about to come out,
yes.
Isn't it? Yeah. So we'll put a link to that into the show notes. And if I'm not mistaken, your book also comes with some program help,
yes.
Isn't it?
Yes, we implemented many programs for application for applying these ranking methods. So we implemented macros for SAS software. We implemented R packages, which are called rankfd, and we have nparld, and another one is nparcomp. So all of these packages, they emphasize on different application areas. So I guess they cover a very broad range of possible data models.
Mm. As you speak about possible data models, so currently we have just discussed very much about the two distribution case, and just I think that is good to kind of grasp the first understanding of the relative treatment effect and these kind of things. But there has been lots of research going on over the recent decades to extend that in many different forms, and there's research in terms of having multiple treatment groups. There's research of having multiple time points. There's research about having also covariates implemented into that. Looking into factorial designs. In terms of that, it's quite flexible now, isn't it?
Yes. So let me go back about the definition of the treatment effect when you have more than two groups. So when you have more than two groups, that's one arising question. So how to define the treatment effect in such a case? So what you do is you need a benchmark. Right? And you want to define a treatment effect, say, first of all, like an effect for every group separately. You need a benchmark, which you define as the average. And then you define an effect for every group to have as the probability that any randomly observation from the specific group is greater than the average. So we did a lot of research going, which goes to the definition of this average. So in standard literature or in previous decades, people defined the average as the weighted mean. So what we did, we found that this definition is not the best way to define the effect at all. First of all, because this weighted mean is weighted by sample sizes, means that your treatment effect later on will also depend on sample sizes, which is not the way how you want to have a fixed model constant in terms of a treatment effect. So that we kept on going with defining the mean as the unweighted mean. So the unweighted mean is a model constant. And then this whole, later on for the estimation, the ranking methods also change. So means if you go then to the estimation that you don't use ranks, but we call it pseudo-ranks. So it's also in our book that we call it rank and pseudo-rank methods. So this just means that you estimate a different kind of a treatment effect for several sample cases or for more advanced models. And we did these approaches, so we generalized these approaches for, as we said, for several samples. This can be any general linear model. This could be factorial longitudinal data. We are working on methods to adjust effects for covariates and baseline values and all these. So there's a lot of research going on, like in my group, then group of Göttingen a little bit, and in Dortmund for Markus Pauli, and some other people who are working in these areas. So it's a very, for me, a very interesting field where a lot of research is going on.
Yeah, I can remember the discussions about pseudo-ranks. I think started about the time I was in Göttingen, where we were looking into this treatment effect a little bit closer. And up to that point, in the about, let's say, mid to end 90s, we always had, this compared treatment effect in terms of a treatment effect compared to the weighted average across all the different treatment groups. Right. So the weighted average of the distributions. And we found that has some nice optimality criteria from kind of sample sizing and powering and precision. Mm-hmm. But of course, it has this downside in terms of the interpretations that if you don't have a completely balanced design, then your treatment effect really depends on this sample sizes and differential sample sizes.
The worst thing, and so, let me add something. What our research is actually, or like the direction of the research that we published. It's also when you said that the treatment effect might depend on sample size or on sample size allocations, then think about the power. So then we found that you might have very surprising, or we call this a little maybe paradox results, or let's use the word surprising results, that the power of these tests highly depend on sample size allocation. So what I mean by this, with all these classical ranking methods, you can set your sample size allocations from your models in a way that you will either get a significant outcome or a significant result or a non-significant, which plays or might play a more important role than the difference in the distributions at all. Right, which is a very huge drawback of this classical ranking methods, and this can be repaired when you define or when you use pseudo ranks.
Okay, yeah, I can see that happening. So, but the interpretation of the pseudo ranks is basically more or less the same of the ranks. Yes. You still get this relative treatment effect, and as a reference is then just the average of all the other treatment groups. So basically, let's say you have 4 treatment groups, and they are defined by different doses of your treatment. Let's say no dose as being the placebo, low dose, middle dose, and high dose. Mm-hmm. And then if you want to compare the high dose, you would compare the high dose versus the other 3 together. So you can say, what's the probability that the highest dose, if you're put on the highest dose, you get a better outcome than if you're randomly put on each of the other 3 doses. Right. That's basically your interpretation, isn't it?
Yes. So you always compare each group, say, to the mean of the other ones. And based on these, if then this probability value, let's say for group number 4 that you said, is the largest, then you can say immediately that then the outcome under dose 4 is larger than under dose 3 and the others.
Yeah. How do that and that similar works now if we have look into time courses, isn't it?
Yes.
So if we look into multiple time points, then we can say, okay, now we not have only 4 distributions for the 4 treatment doses, but we, let's say, have also 5 visits. So in overall, we have now 20 distributions. And you look into each time point and dose, you compare it to all the other time points and all the other doses, basically.
Right.
So you compare one distribution versus the 19 others.
Right. So what you want to have is also for data description, you want to have such an effect size measure for each time and dose combination, right? So and then for this reasons you define the effect that you average all of the distribution under each time point and under each dose, and then compare each cell or each dose and time combination to this mean. And then you have a very intuitive and also very easily interpretable effect size measure.
Yeah, and then from there you can very easily further, derive other things like kind of your average treatment effect across the time points, or your average time effect at a given time point, and these kind of things, where you just average the relative treatment effects, isn't it?
Yes, that's absolutely correct. It's also the way how we do
unweighted average, isn't it?
Yes. So we favor to use the unweighted average of the distributions as a reference distribution when you define the treatment effects. So, and then when you estimate, these naturally leads to the pseudo ranking assignments.
Yeah, I'm just wondering. We just had a call on the real world evidence, real world data. So, isn't this a field where non-parametric could get just based on the data itself? Isn't this a field where non-parametric can get into? And how is it then handled sometimes with missing data in non-parametric approaches?
So, first of all, these ranking methods, these are applicable in broad ranges. It's also from my experience, or I'm lecturing these methods at many places, or where every place has a different field of application. So this is possible. So when you have missing values, we actually work on ways of very effectively incorporate missing values. So what I do, or what we do, is that we define the methods upon all available cases. So implementation is an issue so far when you work in a purely non-parametric field, like to implement missing values. So therefore what we do is to try to derive methods based on all available cases, and then, for example, with good weights based on the information that you have. So we publish a few publications about with missing values. So, but it's research that we actually do, and we're on the way to hopefully one day have very, very nice solutions for this issue.
But basically, you can apply lots of these similar techniques that you would have for parametric analysis as well, isn't it? So you could have, simple imputation methods, or you could derive multiple imputation methods as well, isn't it?
Well, it depends. So when you talk about imputation is usually done based on a model. So you basically usually need a parametric model in the background, and then you estimate the data, right? That's what you do when you impute. You estimate the data, the missing data, based on the information that you have. That goes usually hand in hand with having a certain statistical model. So in this purely non-parametric field, you don't have such a model. So there's not really a model where you can estimate data from. So it might be, if you think about one simple way of just replacing the missing value with the, let's say, the average of the observed observations, that's for sure not the best way to do it, right? I think we all agree. Because you induce a correlation of this imputed value. And then also about how to estimate the rank or the pseudo ranks that this observation, the missing observation, had gotten. it's kind of a field that's not really. It's possible maybe if you assume a very strict missing value mechanism, like missing completely at random, and some more assumptions that there are some works where people relax this assumption a little bit and then trying to impute in, but just for the bivariate case. So this is research that actually is going on, but I'm not very sure there will ever be a very nice solution.
Okay.
So I'm not sure. So I think these non-parametric fields, they have the limitations maybe in these.
But is it really a limitation there, or is it just that, in the parametric world, we, make it easy for us because we just assume a parametric model and then we can work with that. And of course, you could first assume some kind of parametric model to fill your missing data and then move forward with non-parametric approach.
This ranking, let's go back to the point where we ask, so where do the ranks come from? The ranks are nothing else that you put in every observation in the empirical distribution. So when you have missing values, the first question is, which mechanism led to have missing values, right? That we call the missing value mechanism. So now if you have missing values in this ranking, what you need to do, you need to estimate the conditional distribution function given a certain missing value mechanism. What in there you might think or see already that there it's getting very, very complicated. So you can do this when you assume missing completely at random, but as soon as you relax this assumption a little bit and assume missing at random, then the estimation of the distribution function given this missing value mechanism, it becomes very, very complicated. So that's why, and I'm not sure how these things will go when you have even less strict assumptions on the missing value mechanism as missing at random.
Well, I think then the complete estimate discussion kicks in, and you can say, okay, if you think, okay, all these missing data, all these because of dropouts, they are actually treatment failures. You can assign them a certain kind of outcome. Yeah, and then it's a composite strategy, and then you're there. Or if you want to have a treatment policy, then you just kind of further collect these data so that you can make an assumption. So I think that is more kind of a problem that you need to solve on the data itself, and then. For me, the kind of analysis approach is more kind of a second step.
Yeah. There's a lot of research going on. So one of my PhD students, Kerstin, she is working on these pseudo-ranking methods with missing values. So there's research going on, and maybe one day we will have a very nice solution also with let's say, realistic missing value mechanism assumptions. So, but we are there on the first step. So when we have done this, then we keep going and see that maybe one day we will have a very nice solution.
You mentioned a couple of groups working on that. Is there some kind of working group, some kind of special interest groups that is working on that? That people who would be interested in doing research on non-parametric or learning more about non-parametric could join?
So the background for these is the following. Like for me, I worked on these purely non-parametric ranking methods, and then one day I wanted to explore some better approximations to have some better results for small sample sizes. So I started to begin with working with resampling. So and then one day I got in touch with people, like with a research group from Düsseldorf University, where I met Markus Pauli. So Markus Pauli, he was very specializing in resampling and permutation testing. So and that's how collaborative work began. So then he had the expertise on the resampling. I had the expertise on the non-parametric ranking method. So then we began to collaborate and do the resampling and permutation and other works in the ranking framework. And we have some other researchers in the United States and in Canada, where I've been working a lot also with these. So, and it's always when everybody in this research, everybody usually has a different kind of a field where he or she is working on. It depends also on the applications or like in the areas where somebody is working. So for me, it has always been the preclinical trials, and then and some others might do this in let's say in psychological studies. Yeah, and then we meet and then we try to connect these areas. So I think it's very fruitful from my experience, and it's very like for me. I always learn a lot when I get in touch with new research groups, and I can also see how I can like enhance the models that I studied. And you always have new, very like more problems when you generalize the model that you have or like the results that you have to more like to a setting that you never thought about. Yeah, and I think that's how it usually goes.
Okay.
Okay,
very good. Then with that, I think we had a really, really nice discussion about non-parametrics. And as Benjamin mentioned in the beginning, it's close to the hearts of all of us because we have thought about this and worked on it quite a lot very, very early in your career. And you're one of the lucky ones who's continuously working on that. And it's awesome that this research is been going on for quite some time, and it's now in a state where there's a whole complete theory that you can draw from, and that there's software solutions to directly implement things. So that's really, really good. So as a statistician that you're now listening to this episode, think about where these can help you in your day-to-day work. Are there cases where you're thinking, that is maybe not the best approach to just, assume normal distribution? Is there, better ways to do that? And I think that is one of the innovation areas where you can bring new things to your team and where you can maybe have better discussions about treatment effects and what you're actually measuring there and what is really kind of interesting for the outcomes. And for me, especially the composite estimate approach is one of the key areas where we should apply that much more. And especially if it's not just a binary approach, but if we want to have multiple categories depending on why patients drop out, then I think it's a very, very valuable approach. And I think the other ones are kind of outliers and these kind of things. So thanks a lot, Frank, for
Thank you.
Really, really nice interview. And for everybody who's interested in it, check out the show notes. You'll find a link to Frank's work and lots of further work on non-parametric statistics. Thanks so much.
Thank you. Thank you so much for having me.
Frank.
I appreciate it. Thank you.
This show was created in association with PSI. Thanks for listening. Just visit theeffectivestatistician.com to find the show notes that we talked about in the episode today and learn more about our podcast to boost your career as a statistician in the health sector. And especially also check out the homepage of the Effective Statistician Leadership Program. And there you can find all the details that you need to understand who benefits from it. It's actually both supervisors and non-supervisors, and what you can get out of it, as well as help to talk with your supervisor about it. So just go to theeffectivestatistician.com/course. So with that, I'm ending as usual with reach your potential, lead great science, and serve patients. Just be an effective statistician.